Now that we have discussed the concepts of standing waves and some of their physical features, particularly the nodes, let's now apply this to some waves and forms that you're probably familiar with and objects that you might see all the time. So, for example, if I have a string and I tie down both ends, we can say the string is some length L, as I have here. And if both ends are held in place, then that means any vibration I happen to put into the string, it can't possibly move at these points. So, by definition, by holding the strings down like so, those end up being nodes. In between, we don't necessarily know. But if we're going to have a standing wave inside here, and it actually be stable, it must be the case that we have nodes at these points. I could have nodes in between, but I also have to maintain another feature that I have to have basically complete wavelengths or half wavelengths in here. For example, if I were to have some sort of wave in the following form, coming up, going down, and it didn't come to a node, this wave could not survive. It could not be a standing wave. Again, because this point right here is not at a node point. Only way this would work is if the string were not attached there and it's just waving around randomly, and so not a good standing wave there. So instead, let's consider a few different cases. So let's suppose that there are absolutely no nodes in between these 2 points. So we'd only have the 2 nodes at the end, and you would have a line, string line of sorts, that would look something like this. And also from the bottom as well, since it's going to swing up and down like that. So this would be the best case. There's no nodes in between, only at the end, and we do have an antinode in the center here. So what we're looking at is actually half a wavelength, since we have, say, for example, here's the up portion, but we don't also have the down portion. So this is only half a wavelength. So in this smallest case, we'd basically have 1/2 of the wavelength is equal to the entire length of the string. Now let's consider another case. We'll have the same scenario, but in this case, we'll have a node at the 2 ends and one in the middle. In that case, we'll have a shape like this, and also the returning form for the standing wave there. And so our pulse going back and forth, producing that standing wave, and we see there's a full wavelength inside of here. So in this case then, one wavelength is equal to the entire length of the string here. And we can do this with the case of 2 nodes in the center, 3, 4, 5, etc. We can make this as large as you want, and we can actually find then that there's actually a general form to what's going on here, that the wavelength of a standing wave sitting in here is going to depend on an integer amount and equal to 2 times the length of the string divided by n. And here n is going to equal 1, 2, 3, etc. Any nice even integer like that, and also excluding 0, since 0 would be, well, we're dividing by 0, and that's not a good thing to do in any math class. So from our simple constraints of the 2 nodes at the end, we can get these particular harmonics that we call them, where we actually have this thing fitting here. So the first case we had up here, this would be the n equals 1 case, since in that case wavelength was equal to 2L from our equation here, and fits this. So this was the first harmonic, this would be the second harmonic, third, fourth, fifth, etc. So another way of calling the first harmonic we also might call the fundamental harmonic as well. Fundamental frequency, perhaps more often. And of course, if we want to get the frequency, we have to know how fast the wave can actually travel through the string. Combine that with what we know from wavelength, then you can get the frequency. So since we remember that the relationship between velocity and wavelength is this form, we can include our information from how the wavelength here depends on how many nodes we have stuffed in there. And in that case, then, the equation form we get is that the frequency will also depend on our integer n, and that will be the velocity of the wave divided by lambda n. And since we also remember how the velocity depends on the tension and the mass density of our string, we can get the following form where it is going to be n divided by 2L square root tension divided by linear mass density. So this actually tells you two different ways that you can change the frequency on the string. One is that you can increase the length of the string. That will change the frequencies possible, and in particular the fundamental frequency. You could also change the tension, make it tighter, then the frequency will go up. You could also change the string itself, say make it less or more dense. That's actually another way we could put in. And if you were plucking it hard enough, then you could possibly get multiple harmonics on that string as well. But, for example, if you had a guitar string, usually all you're getting is the fundamental frequency, not the higher frequencies as much. So, again, if you have a guitar, one of the ways that you usually tune it is by changing the tension. The little knobs at the end of the guitar change the tension of the line, and that changes the frequency, since it changes the wave speed. All the strings on a guitar are the same length, but you will notice that some of the guitar strings are thicker than others, so you are changing mu. Some guitars also have a mixture between metal strings and nylon strings, depending on if it's a classic guitar, acoustic guitar, things like that. So all the different ways you could change this value, but the thing you'll probably have the greatest amount of control is the tension on there, and using that to affect the fundamental frequency of an instrument like a guitar, same with a piano string, etc. But there's another type of musical instrument we haven't considered, pipe-based systems, or things you might be familiar with, such as clarinets, saxophones, flutes, pipe organs. All those things don't depend on vibrating strings, but instead some sort of cylinder with holes in it usually, but most importantly there's at least one big hole at the end. So if, for example, I have a pipe like so, I could have one end open, like so, and one end closed. Or I could have both ends open. If I had both ends closed, then I really can't get air to travel in there, and I can't really get a pulse of air into there and also get it out and actually hear it. So these are the only two types of instruments you're going to have. If you doubt me, try blowing into a pipe where both ends are closed and make that into a musical instrument. Maybe I should just say save your breath. Okay, so let's again suppose these two pipes are of length L. What are the physical assumptions here? So basically I am going to be putting in pulses of air through there. And what are going to be the limits on the sorts of things that can exist in there that will produce standing waves? Well, for example, if I have this end closed, then no air can really go past this point. It can't vibrate past here. It's like a solid wall in that case. So if I was looking at displacement, since this can't move at all, this would end up being something like a node point. And conversely, at the open ends, then the air is going to move through very freely, and it will have to. If you have a node there, then you really can't get the air to move in and out. There's no reason the air can't move from there. So at these points, we'd actually have antinodes. So for example, the smallest wavelength I could push in there is, again, there's no other nodes in between here, and so you'd get a waveform of something like this. Now the question is, how much of a wave do I have stuffed into there? Well, you see actually it's only a quarter of a wavelength. So at the fundamental frequency, the smallest one I can fit into there, it's a quarter wavelength to the length of this thing, or if you prefer, the wavelength is equal to 4 times the length of the pipe. And here's the strange thing. If I do put another wave in there, if I, say, have a second node inside, oh, yeah, yellow doesn't appear so well. Let's try a nice green palette. Yeah. Green. So we'll have nodes, antinodes, and so you'd have something like so. With my imperfect drawing, you could say. Well, with this setup, you see, okay, here's half a wavelength, here's another quarter wavelength. So we actually then have, in this case, 3/4 of a wavelength is equal to the length of the pipe, and so on. So this is going to have a very different form that you saw before with the string. What about our pipe, though? Our open pipe, if we were to look at that? Well, because of the open ends, we'll have to have displacement antinodes at both. And so there has to be at least one node if we're going to have these two antinodes. So let's say the smallest one we can have is having that node here at the center point. So in this case, what do we have? It may not be as clear as before, but really we have half a wavelength here. So in this case, lambda over 2 is equal to the wavelength. Let me put a bit of a barrier between our equations. And if I were to put another node inside, then I would actually get a full wavelength to pop out. So there are, in fact, 2 different expressions to describe the frequencies in these pipes. It depends on if it's open or closed. So, in the case of the closed pipe, the wavelength, and from that same way then also we'll find that the frequency is defined in the following way. That is going to be n times our velocity, which is the speed of air, divided by 4 times the length, and n can only be an odd number. So 1, 3, 5, 7, etc. And you can see that sort of consequence up here. We went from 1 and then to 3. 2 wasn't possible because the constraints that we had in our setup. While with the open pipe, and by open that means both ends are open, the closed pipe, one end is closed, that fundamental frequency system is going to be n times the velocity of the air divided by 2L, and n can be any positive integer, 1, 2, 3, 4, 5, etc. So the exact same form as we had with the string, but with the closed pipe it is a bit different. So this tells you a couple different ways that you could change the fundamental frequency of a pipe. One, you could make the pipe longer or shorter. That will have a direct effect on the fundamental frequency. You could also change the velocity of the wave through there, and that will require actually changing the medium. So one of the things you may notice is that if you were at a party, you breathe in some helium, your voice changes, it usually gets more high-pitched. Well, your throat is basically a pipe. It's an you could model it as an open pipe, perhaps. And in that case, then, if you change the air in there with helium, which is less dense than normal air, sound waves can actually travel more quickly through that. And so if you increase the wave speed, you're going to increase the frequency, so you have a higher pitch. And if you were to dare and try that with argon gas, which is heavier than normal air, that will decrease the wave speed and you'll have a deeper voice. Argon will be a little bit dangerous because since it's heavier, it kind of sits in your lungs, so it's harder to get out of your lungs. Helium, because it's lighter than air, will more easily get out of your lungs. So not necessarily try that one at home with argon if you have access to it.